It's appropriate to start off this course with a brief introduction to the scientific method. During my years of teaching, I have come to realize that while students have been exposed to this methodology somewhere in their educational program, quite often they're left confused. Confused as to what the actual steps of the process are, how the process is used, but probably even more importantly than that, they tend to be confused as to just why it's so important. Why is this methodology such a cornerstone of science and the way that scientists think, the way that scientists approach their disciplines and their fields? So that's really what we want to focus on in this brief video here today. Let me just start out by saying that the scientific method, which is grounded in the fact that we make these hypotheses or generalized statements that explain things, is really owes its usefulness to the fact that it takes information and facts, measurements, data, observations about our physical world, and puts them in a context that's usable. Information and facts and numbers and figures on their own, no matter how much you accumulate these, really doesn't help us much if those numbers and that data are just sitting there and just don't really form any kind of a context or a story. So the scientific method, by forming these generalizations that kind of tie together these facts, they take what we see, what we observe, what we measure, what we determine through experimentation, and puts it into a package and says, this is what it means, this is how we interpret this information, this is the conclusion that we get from this information, and by doing so makes those numbers useful, makes those facts useful and valuable, and also allows testing and scrutiny and examination by others to see if there's an agreement or disagreement about those numbers and facts and their meaning and how they add to the knowledge that we have of the physical world. So that's really where we're going to head in this video, to try to get a better understanding of that process and how it accomplishes that task of adding to our scientific knowledge. Okay. Again, this process is, like I said, a cornerstone of science. It is founded in fact, in observation, experimentation, testing, measurements, data collection, and then taking that all together and formulating these hypotheses, these conclusions, ultimately theories and laws. We advance what we know in the scientific world. So let's go ahead and look at this process, and let's kind of walk through it step by step, and then we'll kind of give some examples and talk about just how we actually use this method. So the scientific method itself starts out with observations and current knowledge of our physical world. That's just a reality. Right now, when this video is being made, we are here in 2011, and it would be silly or just a waste of time to be looking at information in a critical fashion that we have proven in the past, that we have collected information about, that has undergone scrutiny before, and that we just know to be true at this time. It would be silly for me to spend time, for instance, on examining or studying whether the earth is round or flat. That has been put to bed a long time ago. We understand what's going on now in terms of the physical structure of the world. We have lots of evidence and facts to support that, and so we're not going to bother with that. We're simply going to use that information or knowledge along with current observations to now try to extend ourselves into the areas of the unknown, what we don't know about the world. So as part of that process, we form questions. We ponder about the unknown. We wonder about things that we don't have answers to, formulating questions. I wonder what about, or why is this happening, or what do you think, kind of things. Okay. And as part of that pondering, a result of that pondering about an unknown question, we propose a solution. Okay. So the scientific method says, basically, as you've been considering these questions about unknown items or instances or occurrences in the physical world, propose an answer to your question. And that is what we refer to as the hypothesis. Okay, so the hypothesis is an answer. It's a statement, a generalization that answers the question. Okay, and as such, it should be clear. It should be something that can be measurable and can be tested. Okay? And most importantly, it's not the question itself. Okay? For instance, if in during this scientific method here, using the scientific method, what if part of our pondering and our questions that we were wondering about was, things that are current, such as, what causes global warming, right? Or what causes cancer, right? Those are currently largely unknown questions as far as all the answers to those, and so it might be something that you're pondering. Your hypotheses, what you come up with here in the scientific method that you're then going to test, is not those questions, it's the answer to those questions. It's a possible answer. For instance, you may hypothesize global warming is due to an increase in carbon dioxide emissions. That's a statement that's saying exactly what you think it's due to, not a question. Or in your ponderings about cancer, you may hypothesize cancer is caused by carcinogens in the diet. Okay? Again, an answer, not a question. Okay? So just forming that hypothesis is your start here down the scientific method. And then we design experiments to test it. Whatever your statement is, and as I said, your hypothesis, it should be clear and it should be measurable. And so you set up tests where you can collect evidence, measurements, data that would address your hypothesis. Once your experiment is designed, of course, you perform it, and then you collect those measurements to see, what you find out about your question, about your hypotheses, right? In terms of the global warming, our hypothesis was that the warming, meaning the temperature, is due to something about carbon dioxide emissions. And so you would design an experiment and collect measurements about those two things. Measure the temperature change, measure CO2 emissions, and try to tie those together. Okay. In terms of the cancer, where we said cancer is related to the diet, carcinogens in the diet, again, you would look at carcinogens in the diet, varying the diet, measuring carcinogens, and you would measure or determine in some way, collect information about cancer rates, cancer incidences. All right, so you perform your experiment, okay, and then in the end, once your experiment's performed, you would collect data. You would look at those numbers, those measurements, that data that you collected, and you would evaluate them against your statement, against your hypothesis. Right? If the data seems to agree, right, whatever measurements you've taken when you conducted your experiment supports or confirms your statement as being truthful, as being on the right track, that you have made an accurate statement about whatever you were looking at in your hypothesis, then you would basically say, great, my experiment supports my hypothesis. I have factual reason to believe my hypothesis or my statement is correct. You put that statement out there for the general public, meaning the scientific world generally. You yourself may repeat the experiment and the test to make sure there were no flaws in your methodology. Others, particularly scientists, are going to look at those results, are going to look at the way you conducted your experiment. And one of the hallmarks of science and scientists is that natural skepticism about anything and everything, I should say. And they're going to scrutinize. They're going to scrutinize your experiment. They're going to repeat your experiment and collect their own information, collect their own data, and they're going to try to disprove or find flaw with how you collected your information or your hypothesis, trying their hardest as skeptics to poke a hole in it. Okay. If, however, that kind of repetition, that kind of scrutiny, that kind of skepticism fails to negate your hypothesis, basically everything and everyone and every experimentation that is conducted supports your statement, that statement may eventually be accepted at the level of a theory or a law in science, two levels, kind of higher than a hypothesis, that acknowledge the fact that this statement, this generalization, this basically information about the world, this new knowledge about how the world and how the world works, has withstood scientific scrutiny, and it has, validity for that reason. Okay. On the other hand, if through this process, when you conduct your experiment and you collect your measurements and your data, they're inconclusive or they contradict your hypothesis, then you have no recourse but to reject your hypothesis and try to think of a new reason, a new statement, a new generalization that answers your question that you can then approach scientifically to collect information to support or reject. Okay. As you can see, this is a very iterative process. It does take a lot of time. It's performed under very rigorous conditions. The scrutiny and the skepticism that's involved in these experiments take time also. It is a very reflective process. And so it does take a long time for us to advance our scientific understanding of the physical world and increase our knowledge base in science. That's just simply part and parcel with the discipline. Okay, just to make sure that we're kind of good with all of this, because and solid with the scientific method, let's kind of look at a little just kind of example, something that has nothing to do with biology or the fact that you may what fields of science you've studied already. Let's just take something familiar to most people. When I walk to my classroom every day to teach, I have noticed that there's frequently puddles on the sidewalk. We're all very familiar with puddles. You've seen puddles in front of your house, in front of where you live, on your way to work also, and we know something about them. This is our current knowledge. We know they're made of water. We know that there are things that could affect the puddles. We know, and we may notice as I walk to work, that sometimes the puddle is larger, sometimes the puddle is smaller, and so that kind of forms my current knowledge and my questioning. I may question and ponder. Why is the puddle different sizes on different days? What's causing that? How come it's bigger or smaller depending on the day when I walk by it? Okay, and so it would be appropriate, since I have a question and I don't have an answer to it, to form a hypothesis on this. Okay, so a very simple hypothesis here would be that the puddle size is directly related to the amount of rainfall. I've noticed that it changes with rain as I walk to school, as I walk to my classroom, and so I may want to use that as my hypothesis and say, I think that the reason that puddle changes in size is directly related to the amount of rainfall that's happening in the area. So then I would go ahead and I would design an experiment to test that. As the scientist, I get a little leeway in the design of my experiment. I get to select what puddle I'm going to observe. I get to select how long I want to conduct my experiment. Do I want it for a week, a month, a year? What time of day do I want to collect my data? How exactly I'll collect my data? Will I go out there with a measuring stick and measure my puddle, or am I going to be worried about the depth or the width of it, or what measurements do I want? How am I going to measure the amount of rainfall, because that's my the other piece of information here. Not only is it the puddle size, which I'm trying to figure out, but I'm trying to figure out how that relates to the amount of rainfall, the actual amount of rainfall. And all of that I get to do to design my experiment. Then, of course, once I've designed it, I would actually conduct the experiment, and I would collect numbers. I would collect the size of the puddle, however I've decided to do that. I would collect information on the amount of rainfall, and I would then evaluate those results. Do the numbers that I have, do the measurements and the data I've collected support the fact that rainfall seems to be critical and a determining factor in the size of my puddle, or doesn't it? Okay. All right, so that's kind of just taking through a normal, an easy process here, an easy example of the scientific method. But let's try to look at this just a little bit further then. What do we think in terms of this simple experiment, this simple hypothesis? Do you think that I'm really going to end up with numbers, measurements, and data that support my hypothesis or not? Okay. what I'm hoping or what I'm thinking is that several of you watching this video, back when we did the very first beginning of this example, and I said, what can affect the puddle size here? I'm wondering, I'm curious, I notice it changes. You may have come up with something other than rainfall. You may have thought of something else that would have been your hypothesis. Maybe you thought about the fact that it could be temperature. You weren't thinking rainfall, you were thinking temperature. Or maybe you were thinking it was going to be amount of sunlight. Right? Different times of the year, different amounts of cloudy or sunny days. Maybe you were thinking something like, gee, there could be sprinklers in the area. And these sprinklers could be affecting the amount and the type of puddle size. Or maybe you thought of traffic, right? Are there some children that are running through my puddle in between the days that I come by and do my measurements, right? A whole variety of things that you may have identified as influences on that puddle size that wasn't the one that I put in my hypothesis. On my hypothesis, I chose rainfall. Okay? Those additional factors that could influence the puddle size and influence your experiment are what we refer to as variables. And they are very important to consider in the formation of your hypothesis and in the design of your experiment. Okay? These additional variables that are not the primary focus of the hypothesis must be controlled. Okay? And that, I cannot stress that enough. Not only the importance of doing it, but also sometimes the difficulty of doing that, right? When we set up our puddle experiment here to see if it was rainfall that affected the puddle size, the fact that we were cognizant of these other factors that could affect it means that I have the responsibility as the scientist conducting this experiment to acknowledge those other factors, those other variables, and control for those. I have to establish in my scientific design, the experimental design, how I will make sure that the temperature, the sunlight, the sprinklers, the traffic, or any other variables that can be identified as having a potential effect do not enter into my experiment. And that's quite often a difficult thing to do. And I will say straight up that quite often is one of the reasons that we see in science that sometimes hypotheses are questioned, either initially at the initial level of scrutiny by others. Other individuals may recognize variables that were not controlled in your experiment. Say, for instance, if I had controlled in my experiment temperature, amount of sunlight, and sprinklers, but I had not thought of or recognized that kids coming through my puddle might have an influence, another scientist who recognizes that fact would question my experiment and say, you need to be cognizant, you need to have that other variable controlled, go back and do it again and make sure that there are no kids running through your puddles on the days where you're not guarding your puddle. Okay? And so we do see this in science. We see immediately that level of scrutiny. We also sometimes see after the fact. After the fact, years later, some piece of scientific information that has been derived by following the scientific method, that a scientist did go through these steps, did come up with a hypothesis, and the data did support that hypothesis, and we now believe that that's a new piece of scientific information, a new piece of our knowledge, may be called into question at a later date. One reason quite often is some variable or factor that was not known at the time and has been realized later and now calls into question, was the scientific experiment that you did that gave us that knowledge done under controlled conditions for this new variable, for this new factor that we've just recently identified? And so we will sometimes see a little back and forth. Sometimes we'll see retractions in science. I'm sure you've all witnessed these kinds of things where you'll read something that scientists now know X, Y, and Z, and 3 years later, that will be called into question. And quite often the reason is not that the scientists were unethical. It's not that the scientists didn't follow the scientific method when they conducted their studies and originally came up with their information. Quite often it's due to the fact that some variable, something that could influence the results, was recognized at a later time, and now that calls that study into question. Okay. But in the end, hopefully, as you've seen through this video, through this brief video and discussion, this process, right, which is a very rigorous process, done in a very analytical fashion, scrutinized by others, faced by skepticism by others, repeated and done exhaustively to determine that everything that we could think of, every nuance, every factor, every variable has been controlled. In the end, that process, that methodology results in validating conclusions, validating hypotheses, statements that give us new information, generalizations about our physical world.